Hello students, we ended up at the linear expansion coefficient topic. So today we will be starting up with the volume expansion coefficient. Okay. As I told you, volume expansion coefficient happens when we are talking in three dimensions. This means expansion in the substance is occurring along x-axis, y-axis and z-axis. So the linear dimensions of an object are changing with temperature, but along the all three dimensions, that is called as volume expansion. And the coefficient corresponding to this volume expansion is taken as beta. Like we took alpha for the linear expansion coefficient in the last video. So in this video, we are talking about volume expansion. Again, the volume expansion is directly proportional to the temperature difference or temperature change of the substance. It also is directly proportional to the initial volume of the substance. And when we club both of them, we get this kind of equation where beta is the average coefficient of volume expansion and it's a constant quantity. This constant quantity is also defined as per the nature of material which is assumed. Okay. So to find the relation between beta and alpha, we want to develop how linear expansion coefficient and volume expansion coefficients are correlated with each other. We will be assuming our material to be isotropic in nature. Okay. Isotropic means along any direction the material properties are remaining same. That is called an isotropic material. Normally amorphous substances, they are isotropic in nature. So let's consider a box of dimension length L, width W and height H. Its volume will be, initial volume will be length multiply width multiply height Vi, that is the temperature Ti. If temperature is increased to delta T amount, so final temperature will be Ti plus delta T and its volume expansion, for example, occurred as delta V. So final volume will be Vi plus delta V. So each dimension is changing along x, y and z. So we can say delta x increment, delta y and delta z increment occurred along x, y and z axis. Okay. So let us consider the equation for that. Simply, Vi plus delta V can be written as, the volume is increasing, getting increased by delta V amount. So we can write as Vi was equal to L multiply W multiply H. So Vi plus delta V can be written as L plus delta L multiply W plus delta W multiply H plus delta H. Every increment is added into its own x-axis, y and z-axis. Again, we knew that as per the linear expansion coefficient, delta L was equal to alpha Li, that is the initial length, into temperature difference T. That was for the linear expansion coefficient. So I'm putting those values inside these expression delta L, delta W and delta H value using the linear expansion coefficient expression. On putting these values, take L, W and H as common outside because it's coming in every expression, and within the bracket you will get 1 plus alpha delta T whole cube. Now putting the formula of A plus B whole cube, we know as per the maths, it's equal to A cube plus B cube plus 3A square B plus 3AB square. Now putting these values here, we have reached up to this particular equation. Vi times 1 plus 3 alpha delta T plus 3 alpha delta T whole square plus alpha delta T whole cube. So this is the final volume which is attained. Now let us simplify this equation by a simple process like dividing the whole equation by Vi term. Once you divide it, this will become 1, this will be again 1. The delta V by Vi is coming here. Plus 1 is here, minus 1 is here, they will get cancelled out. So 1 has been eliminated from this equation. 3 alpha delta T, 3 alpha delta T square plus alpha delta T cube. So we have got an expression till the third order. Now, as we have considered delta T change to be less than and comparable to 100 degrees Celsius. So delta T is very less than 1 actually. So what we can do, we can actually neglect the higher order terms. And alpha value normally ranges in the power of 10 to the power minus 5. The range is like this. So once you multiply alpha by delta t, it will be a very small value. So the higher order terms can be neglected. On neglecting these higher order terms, alpha delta t whole square and cube, we are only left out with the first order of equation. So delta v by vi is equal to 3 alpha delta t. But we also assumed in the initial that obviously our change in volume is equal to beta times of vi into delta t. So on comparing these two equations, we can easily say that actually beta is coming out to be equal to 3 alpha. See, in the previous slide, we took in the first one delta V is equal to beta Vi delta T. That is the dependency of expanded volume depending on the change in temperature and initial volume. So on comparing the two equations, we have developed a relationship between the volume expansion coefficient beta and linear expansion coefficient alpha, and these are constant which are depending on the nature of material. So if you know the alpha for steel substance, how they will react in the heat, then you can easily say that if we are talking about as a whole volume, so beta will be 3 times of alpha, like this. Okay. Similarly, we dealt surface area expansion coefficient is not there in the syllabus, but yes, we can also derive it, and the expression comes out to be 2 times because we are talking in 2 dimensions. So 1 dimension in 1 alpha, 2 dimension 2 alpha, and 3 dimension is 3 times of alpha. That as simple as the correlation can be developed. Okay. So these are the diagrammatic representation of how we can show the expansions along linear, along one dimension. Expression is given out to be here. If we talk about the area expansion term, again along two axes, the delta A upon A, where A is the initial area, initial length Li, and initial volume Vi, and then again comes the coefficients alpha, 2 alpha, and 3 alpha based on the dimensions, and delta T. What change in temperature has brought up these changes in the expansions in the substances? Why they are expanding? Because of the only one phenomenon, that is the heat, which is leading to thermal expansions in the material. Okay. Okay, class. So this is a numerical which I want to explain you. It is based on this concept only. It states that a segment of steel railroad track has a length 330 meter when the temperature is 0 degree Celsius. What is the length when temperature is 40 degrees Celsius? So in this again the linear expansion is being talked about, an alpha value for steel is given out to be 11 to 10 to the power minus 6 per degree Celsius. So we will evaluate a length increase using the previous slides discussion only. Okay. So simply what we will do, we will take the linear expansion is actually given by alpha times of Li delta T. Alpha value is 11 into 10 to power minus 6 here, and then multiply with the original length, which is 30 meter, and then multiply it with the change in temperature. The change in temperature is 40 degree minus 0 degree Celsius. So this much. So simply on solving this, we can reduce the expression 3 for the 12 and 12 into 11. So it is coming out to be 0.013 meter. This is per degree Celsius. This is getting cancelled. The change in length, linear expansion is 0.013 meters. So we can say that new length of this railroad track will be, original is 30, calculated linear expanded length is 0.013. So total length is 30.013 meters. This is our answer. Okay, this is how we can solve this. Yeah. The next question talks about the thermal electrical short is given that two bolts are attached to a different parts of an electrical device. and they are almost touching when the temperature is 27 degrees Celsius. As the temperature increases, the intervals move towards each other. So this much gap is there between the steel and the brass. So what we have to do, we have to, so a poorly designed, it has two bolts, it is there. The initial gap between the ends is D5 micrometer. Initial gap is this. This is at 27 degrees Celsius. The gap is at 27 degrees Celsius. So we have to calculate temperature at which they will expand to this much part. So expansion term is given here, right? So we will write, we will use that formula delta L, linear expansion for brass. Obviously it will different from the steel. Alpha will be different. So we will take them separately. So alpha brass times initial length of brass Li Br, and then change in temperature plus alpha steel, the initial length of steel, and delta T is actually giving you the total expansion term. So by taking the delta T common on these, on the both the sides, the delta T common in the bracket, what will come? Alpha brass plus Li alpha steel for brass, and Li initial length for steel is actually equal to D. And we can see that expansion is total 5 micrometer. So let's put the value of D, 5 micrometer, 10 to the power minus 6 meter, and then putting the value here, the change in temperature which is required to make both of them join and cover a distance of 5 micrometer. So let's put the value. Alpha of steel we already had taken, it is equal to, okay, first brass is coming, alpha B of brass is 19 into 10 to power minus 6 degrees Celsius inverse, multiply by, it is a multiplication sign here, it is a multiplication sign, length, initial length of brass, which is equal to 0.03 meter, added on to 11 into 10 to power minus 6 multiplied by 0.01 meter. Okay, again this is degree Celsius inverse and meter is coming here. Meter is coming here. So meter will get cancelled from the numerator and denominator. Degree Celsius inverse will go up and become degree Celsius. So on calculating this, it's come out to be equal to, when you do the calculation, it come out to be equal to 7.4 degrees Celsius. So this much temperature must be increased. So if initial temperature was taken 27 degrees Celsius, Pi was 27 degrees Celsius, so final temperature attained will be 27 plus 10.4, which would be equal to, you can say 14, so 34.4 degrees Celsius. That's a final temperature which needs to be maintained for them to join at that particular point, and where steel and brass will, the gap will become 0. Okay. Okay class, we talked about the volume expansion coefficient and did some numericals on linear expansion and volume expansion coefficient in this particular lecture. So we will continue with the other topics, that is, those are equation of state and further topics in the next lecture. Thank you so much.